Okay, I would like to make an overview of MHD instabilities. So this video is based on the intro to plasma physics. By Chen. I think the full name is like Intro to Plasma Physics and Controlled Fusion. But anyway, so basically almost all of them are following the same recipe. First, they have a MHD equation. Yeah, for the purpose of this video, we'll assume use isothermal. And one is perturbed term, so we basically just we assume equilibrium is blah blah blah. There's other first equilibrium terms that is just basically just that is homogeneous and also time independent. So and based on this equation we can have and continuity equation. And also we assume all those quantities, all those perturbed quantities is a plane wave. And then we will arrive to a dispersion relations. So for the first and foremost, let's study electron wave. So basically, we only studied the MHD equations for only electron species, and we assume we don't have a magnetic field. So we're basically solving a one-dimensional MHD equation. Then we can, after solving it, we will have Just keep in mind this is in SI unit. So this will be used over and over again in a lot of approximations. So here it is. And the second one, we go a step further. This is plasma oscillation, and we do a plasma wave. So previously we only considered the perturbed term, so this will only give us, on the right hand side will only give us the electric force. And for plasma wave, we will include the pressure gradient term. Then we will have a dispersion relations expressed in the following way. So wave thermal is defined as 2kT over kBT over m. That's a big K, that's small k. Small k is wave number, big K is Boltzmann constant. So as you can see, when we go to the large wavelength, so this wave number is small, then it's become a purely plasma wave. And when we go to small wavelength, the wave number is big, then it becomes purely thermal based, which I think is quite interesting. And then the book talked about sound wave, sorry. So basically we just study ion with B not equal to 0, and including the pressure gradient, because sound wave is induced by the pressure gradient. And we even assume that we don't have no electric field, because basically this is just based on the purely fluid dynamic. So we have a phase velocity of gamma kt over m. Big M stands for ion mass. This is speed of sound. So after that, we study the ion wave. So B not equals 0 and E. We include the electric field and we include the pressure gradient. So relatively to the electron wave, where we are having a different density, which is quite curious. We're basically just using the Dirac-Schelling expression. That will give us basically take the first term of the first two terms, so that we will have the perturbed term will be this. So as you can see, the potential is coming from the electron instead of ion because ion is so massive. Then we will arrive to a speed of sound in plasma. Well, I should put it here. KTE gamma I KTI temperature electron temperature of ion mass of ion square root. That's the speed of sound in the plasma. Well, which will be also used in the a lot of simplification. So after that we study width. So after that we will just go to B naught not equal to 0. So the next one, we study electron. Sorry, I have to check if it's still recording. I think it is. The electrostatic oscillation means K is perpendicular to the B naught. So we assume B naught Z, the Z direction, K is an X direction, just for simplicity. And you will have basically, instead of one-dimensional solution, which is from 1 to 4, we will have a two-dimensional equation. So we will end up having omega equals to omega p square plus omega c square, where omega c is the cyclotron frequency. Recall from kindergartens we learned that the cyclotron frequency is this. So yeah, we can think of if the density is so low, then it just become a single particle motion, which is gyro motion. When the magnetic field is not so strong, but the density is so high, then it's become purely plasma motion, like just no magnetic field. So this thing is called upper hybrid mode. And for ion, we have a similar result. They're almost perpendicular, but not quite, as mentioned in the literature in Chen's book. So we have another kind of similar hybrid mode. Big omega c, that's a cyclotron frequency for ion, and k square vx square, that's speed of sound in plasma. So if you consider both species and that together, you will have a lower hybrid mode. So this is those things. You can use you got those expressions from. Basically, the Bill Savard. Oh, what's the name? I just can never remember those names. So you get from this is Ampere's law. Yeah, and impose the plane wave approximation, and you get nice relations to simplify, to reduce your equations. So there we have several simple ones, and now we can study a really interesting one, because we can use this equation to this relations to basically, in a way, have a further higher order motion. Correct me if I'm wrong, because I could well be wrong in terms of plasma physics, since I'm just first year grad student. So K is Z direction, B is D direction, and just for simplicity, we can just assume like, sorry, it doesn't just have one direction. You will have, well, you could, and then you solve those equations. You have wound up having relations like that. And you can make a further approximation. The permittivity is big, really big. and you will have phase velocity can be expressed in a really simple form. And that is our film velocity. And you basically, this is for ion, and for electromagnetic wave, and then you add, like this is only you just neglect pretty much neglect the thermal motion. If you add a thermal motion in it, and at least that's my understanding, if you add a thermal motion and use continuities equations, you will have a new dispersion relations. This is really painful to derive. I did it once, 3 times, sorry. So there we have it. That's all the, this is not, this is sonic wave. Is for for low frequency electromagnetic wave, and this is also for low frequency as well. It's low frequency. Yeah, this is for low frequency. Those are for higher frequency because they this whole derivation we constantly impose such approximation simplification. The cyclotron frequency is way bigger, larger than the mode frequency. But yeah, that's what we have, and just a quick overview. So here is electron frequency, electron wave. It is basically in a without any thermal motion with homogeneous background. Basically, it just have nothing. It's basically the plasma has this with certain density. It will have this intrinsic frequency. If you excite it, it will just excite to that specific frequency. And you add a temperature factor to it, you will basically have the plasma frequency competing with the thermal motion. This is a good old sound wave. It doesn't have basically just the driven force is a pressure gradient, and then it basically you can think of these you push forward something, it will that's the velocity it will travel through the medium. It's not necessarily need to be plasma, but on the other hand, in plasma we will have this frequency which will be modified, which will be modified by the electron temperature because if the ion is moving, electron will relatively fastly catch on to the ion motion because the small mass of the electron. Then it will create somewhat a drag force in a way. Drag force or pushing force. For those these are all like no magnetic field, no background magnetic field. If we have a homogeneous large magnetic field, we will have a upper hybrid mode, which is competing between the cyclotron frequency and plasma frequency. It's all looks like the similar form, which is interesting, and that's what electron for ion is basically competing between thermal motion and cyclotron motion or gyro motion. And once we go to the low frequency, this for ion, then we have a affine mode. So affine wave, and it is basically induced by the perpendicular current, Jx, which I may talk about in the future, but yes. The magnetosonic wave, which basically how the electron how low frequency electromagnetic wave will propagate in plasma with non-zero magnetic field. As you can see, it's just adding to all the factors that it is considering to, because if you essentially electromagnetic wave is oscillating is oscillating. It's basically giving a perturbed electromagnetic field. It will give us. It will induce. It will basically in a way competing with affine wave. As you can see right here, is really interesting, such that is resemble really closely to the other mode, say like homogeneous non-magnetic with magnetic field, homogeneous. Yes, so that's what I want to talk about for the quick overview of MHD instabilities. And of course there's more to it, and I would like to know more because I'm trying to prepare myself for a qualifier. If you have more material to suggest, please tell me. Some papers, some books. Yeah, thank you.